Hello everyone, I'm Pratish. I'll talk about cloud-hosted financial exchanges. In this talk, I'll present a simple mechanism called DBO that ensures fairness among competing traders in cloud environments. Recently, there has been a lot of interest to move financial exchanges from on-premise to the cloud. Several exchanges and cloud providers have announced business partnerships to this end. Now, there are several reasons for this interest. For example, lower costs. Now, before any exchange can move to the cloud, there are a few technological barriers that need to be overcome. One such fundamental barrier is fairness. To understand why, let's see how an exchange works. The central exchange server produces market data continuously and sends it out to various participants. The market participants use this data to generate trades. These trades are processed by the exchange server in a first in, first out manner. A critical clientele for exchanges is high-frequency traders such as citadels. These traders are engaged in speed races where they're competing for the same trading opportunity. There's an arms race in high-frequency traders to respond to the market data the fastest and win the speed race. In these settings, even minor disadvantages in networking latency can change the outcome of a speed race and kill competition completely. To enable fairness, exchanges today have over-engineered their on-premise networks to provide equal bidirectional latency between the exchange server and the participants. This way, the market data is delivered simultaneously to all participants, and trades are executed in the order that they were generated. These two properties together ensure fair competition. As I mentioned earlier, moving to the cloud remains a dream as of now. In particular, unlike on-prem data centers, it is very hard to ensure equal latency in cloud. There are many reasons. For example, the wavelength of the cables might differ, there might be congestion in the network, or additional delays at the end host. As a result, it is very difficult to ensure simultaneous delivery of market data. Recently, there has been a proposal called CloudX, which proposes using clock synchronization to achieve simultaneous delivery of data in cloud. The CloudX solution works as follows. Corresponding to each participant, there's a co-located release buffer. These release buffers are clock synchronized and are responsible for releasing data simultaneously. In particular, market data generated at a particular time is released by the release buffers at a later pre-specified threshold. For incoming trades, the release buffer marks a timestamp corresponding to time the trade was generated. The ordering buffer orders these trades based on this generation time before forwarding them to the exchange. This way, the solution facilitates fair competition. Now, there are two fundamental problems in using clock synchronization. The first one is already known, that it is hard to achieve perfect clock synchronization. The second one is that even with perfectly synchronized clocks, it is hard to ensure simultaneous delivery of data. When network latency spikes beyond the latency threshold, this solution incurs unfairness. In our paper, we proved that simultaneous delivery of market data is actually impossible in environments with unbounded latency. This result is a simple consequence of the classical two-chip rules problem. So, given these challenges, how do we achieve fairness? One solution is to re-architect the cloud networks to provide perfect clock synchronization and bounded latency. In this talk, we do not re-architect the cloud. Our solution, delivery-based ordering or DBO, takes a fundamentally different approach to achieve fairness in the existing cloud. In DBO, we don't try to achieve simultaneous delivery. Instead, we achieve fairness for correcting for latency differences in delivery of market data. This post-hoc correction approach has some really nice advantages. DBO provides guaranteed fairness for speed racing in existing cloud networks without requiring any clock synchronization or bounded latency. Further, DBO achieves fairness at low latency. To understand how we correct for latency differences, let's look at how a speed race works. In a speed race, multiple participants compete for the same trading opportunity. A particular market data point serves as a trigger for the speed race. The outcome of the race is determined by the order in which competing trades of the speed race are processed. The figure here shows an example of a speed race that is triggered by data point X. The figure also shows the response time. That is the time it took the participant to respond to the trigger. Now, since the outcome of speed race is determined by the order in which trades are processed, to achieve fairness, all we need to do is order competing trades of a speed race based on the response time. So in this example, trade from participant 2 should be ordered before trade from participant 1 to ensure fairness. We refer to this kind of fairness as response time fairness. It turns out it is also impossible to achieve response time fairness in network environments with unbounded latency. This theorem is a consequence of the fact that the trigger point of a trade is unknown and the classical degenerate problem. What DBO guarantees is a slightly weaker form of fairness called limited horizon response time fairness, or LRTF. As per LRTF, only trades with response lower than a certain threshold are ordered fairly according to their response time. LRTF is still a useful guarantee as most high-frequency traders respond fast, typically within a few microseconds. I'll now give a high-level overview of DBO. Our approach is inspired by the use of logical clocks to correct for latency differences while ordering events. Now, DBO introduces a new kind of logical clock called delivery clock to order trades fairly. The overall architecture of DBO is similar to that of CloudX. Each release buffer maintains a separate delivery clock. The release buffer marks incoming trades with the delivery clock timestamp at the generation time. The trades are ordered at the ordering buffer using this delivery clock timestamp. At a high level, what the delivery clock does is that it tracks time relative to the delivery of market data at the participant. Formally, delivery clock is a lexicographical tuple, where the first element corresponds to the last data point delivered to the participant. The second entry measures the time elapsed since the delivery of the last market data point. I will now show you how delivery clocks can help correct for latency differences in delivery of market data. Consider the simple speed race triggered by data point X. In this example, delivery clock of participant 1 will read the following at the time of trade generation. Similarly, delivery clock of participant 2 will read the following. Now, since response time of participant 2 is lower, the delivery clock of participant 2 will be lower than delivery clock of participant 1, and trade from participant 2 will be correctly ordered ahead. This way, the delivery clock is able to correct for latency differences and order trades fairly. Note that the delivery clock on its own does not provide fairness in all scenarios. In DBO, the exchange server actually batches data, and the release buffer paces the delivery of these batch data. With batching and pacing, DBO provides guaranteed LRTF. For details, please see the paper. To evaluate DBO, we did a cloud-based evaluation. Our experiment consists of 10 participants. This table shows the latency numbers for DBO. It also shows what fraction of trades were ordered fairly. This table also includes results for direct delivery, but there are no ordering or release buffers. As expected, direct delivery achieves poor performance because of variations in networking delay across participants. In contrast, DBO achieves 100% fairness. In this table, we also report the max RTT across all participants. In our paper, we show that this max RTT is the minimum latency required to achieve response time fairness. DBO's latency is actually close to this bound, with additional delay added due to batching and pacing. In this experiment, thus, DBO provides perfect fairness at sub-100 microsecond cloud latency. To compare against CloudX, we use simulations. This figure reports the fairness and average latency numbers. For CloudX, we report the results across different latency thresholds. DBO achieves perfect fairness at much lower latency. To recap, I presented DBO, the first mechanism that enables guaranteed fair speed racing in existing cloud networks. Our evaluation shows that DBO can achieve sub-100 microsecond latency in the cloud. Under the hood, DBO uses logical delivery clocks to correct for latency differences in delivery of market data. With this, I'll stop. Thank you.